My name is Viktor Zverovic, and I'm a software engineer at Facebook. I'll be talking today about a modern formatting library for C++, and it has nothing whatsoever to do with my work at Facebook. In fact, I started this project long before I joined Facebook, and I worked on it in my spare time mostly. First, a bit of wisdom from one of the reviewers of my CppCon submission. So formatting is something everybody uses, but nobody has put much effort to learn. And I hope very much that you'll learn something from this talk. So here's a brief high-level overview of what formatting facilities we have in C++. Obviously, we have two standard solutions, stdio and IOStreams. And we have a bunch of formatting libraries like bootstore format and fast format, arguably two most well-known libraries. And I also included Foley format. It's not a separate library, but a part of Facebook Foley, which provides formatting facilities. I included it here because it's very relevant to what I'll be talking about. And there are millions of other ways of doing formatting. Pretty much every large code base has their own safe printf replacement for various definitions of safe. And I'll go in roughly chronological order, starting from the past, stdio, which we inherited from the C standard library. And here's a warm-up trivial example, and also to calibrate the audience and see how many of you are sleeping or checking emails, and how many of you are awake. So who thinks that there is an error in this slide?
I don't think there's an error in the slide. There's an error in the code.
In the code. Yeah, this is correct. Who thinks that this is okay? This code is fine. Okay. One person thinks that it's fine. Yeah. So obviously there is a mismatch between the argument type and the format specifier, which is %s, which assumes that the argument should be a C string or null-terminated string. And good compilers like GCC or Clang will warn you eagerly and give lots of useful details. They even say which format specifier you can use instead. And this is great, but unfortunately it only works for literal format strings. And in reality, they can be dynamic. They can come from, especially due to localization. So another problem is memory safety. Let's assume that you want to format an integer, and you went to great lengths to compute exactly how many characters you think you need to allocate for a buffer. So you even added 1 for terminating null character, and this is the common source of errors, of course, and you allocated the vector of this size, and you passed this buffer to sprintf together with the format string and an argument, where x is the same as before. It's an integer, and you store the return value in the result variable. So who thinks that this code is correct? Okay, good. Who thinks that it's incorrect? Okay, yeah, this is incorrect. And if we want to check and print the result +1 for null terminator and the size, most of the time it will kind of work, but for over 1 billion of integers, if you use 32-bit platform, you'll get output 1211, which means that you have a buffer overflow. And obviously, it will happen for integers less or equal to minus 1 billion, because we didn't take into account the minus sign. And solution is to use SNPrintf, but unfortunately it cannot grow buffer dynamically, so you either need to precompute size or overestimate the size, which is suboptimal. And did you notice another error on the previous slide? Not the writing past the end of the buffer, but something else. So to kind of remind you, here we computed size, we returned the results. So did you see any errors, any more errors in this simple line of code? Yes, exactly. So the size t, and compiler again gives you this nice warning message, except that in this case it's incorrect. So the correct specifier for size t is not %lu, but %zu. So yeah, and then you can get errors like this, which is an actual screenshot from a bug report to a game called Cataclysm, if I read the ASCII art font correctly, where you can see lots of ZUs, which I don't think are intentional there. And this is pretty recent. This is opened in 2016, this bug report. And the problem was that they used Visual Studio, which didn't support %zu until like version 2015, I believe. And we have the whole zoo of macros for fixed-sized integer types that define different format specifiers. This table I took from CppReference.com. And the worst thing about these macros is that to use them, you have to break the string, insert the macro, and then continue your string, which is horrible. I don't even know how would you use that with a non-literal string. So why do we need to pass type information manually if the compiler knows the types? So the answer is, of course, varargs, which are so old they have been featured on the History channel. So for a long time, I believed that varargs must be super fast at C, right? It's the best. But then I looked at the actual generated assembly code and kind of did some benchmark. So what I found out that on some platforms, at least, maybe on all platforms, they are non-inlineable. Well, functions that use varargs are non-inlineable, and also they produce a bunch of code to store the registers on the stack. This seems insignificant, so we can measure what's the impact. So it's just a few %, not very important, but annoying. And also, if you optimize the underlying printf implementation, which can be done, and I have an alternative implementation, which is somewhat faster, then this difference will be more profound. So a more serious problem is lack of random access. So if you use positional arguments, you'll need to set up extra arrays. And printf does a bunch of other stuff. So on my platform, which is macOS with Clang, if you use positional arguments with sprintf, it can be almost 2 times slower, which is crazy. What can we learn from it? So we can learn that varargs is a poor choice for modern formatting API because of manual type management. They don't play well with positional arguments due to lack of random access. And we have suboptimal code generation, and the functions are non-inlineable. So we can do much better with variadic templates. So now the question, why even bother about varargs? This is ancient stuff. The reason is that I saw many times people write safe printf replacement on top of sprintf. So they solve some of the issues, but not all of them, and often add extra layer of overhead by performing these type checks. So I think it's better to go and kind of start from scratch and use variadic templates kind of in the first place. And finally, in this historical section, I'd like to talk a bit about extensibility. There is no standard way to extend printf. By extending, I mean supporting formatting of your own types. But there is a GNU extension, and as you might imagine, it's pretty horrible. So to use it, you need to register two functions. One that actually does formatting. Here it's called print widget, and it does an unsafe cast there, and it's supposed to format the object that you passed in. And the other is kind of type checking function, although the only thing that it does, it just says that the argument should be some kind of a pointer, which is not very type safe. And moreover, if I remember correctly, they recommend only using uppercase letters when registering handlers for new types. So if you ever want to support formatting more than 26 types in your program, you're out of luck. This brings us to the present, or IOStreams, which is the standard C++ way of doing formatting and I/O. And while it solves lots of problems with printf that we saw earlier, it has problems of its own. One of the most obvious thing is what Matthew Wilson, the author of Fast Format, called chevron hell, which I think is a very good description. So here we have two snippets of code that do pretty much the same formatting. So one uses printf and other uses IOStreams. So who prefers the printf version? Okay. Who prefers the IOStreams version? Oh, have a few hands there. But the majority seem to prefer printf. So if we put aside all the issues with it, obviously the code is much more compact and readable. And finally, C++ 11 gave in to format specifiers for time and introduced the std put time function. There are some differences in these two pieces of code, which I will talk about later. So another issue that we have with IOStreams is problems with translations. So if we use printf, we have the whole message with arguments available for translation. But in IOStreams, by design, parts of message are interleaved with formatting arguments. And the thing is, in general, translation of the formatted message is not equal to the concatenation of translated parts, at least in many languages. It doesn't mean that the formatting library should provide translation facilities, but it should be possible to build them on top of the provided API. Other problems related to this is reordering of arguments and access to arguments for pluralization. So now let's take a look at I/O manipulators. So in the first line, we just print out some integer in hexadecimal, and then we try to print something else. So what do you think the second line will print out? Who thinks it will print out 42? No? Oh, good. What do you think it will print out? Yes, exactly. So it will print out 2A, obviously, because we didn't switch back to decimal. And some flags are sticky, some are not, so go figure. And the solution to this problem is to use Boost.io iOS flag saver, but it's a bit annoying. So I think that ideally, formatting functions, when you call them, they shouldn't produce any side effects other than the output itself. And here, in this example, we're trying to write a little bit of JSON. And we can do it manually, like in this trivial example, or we can use one of the tons of JSON serialization libraries, and which underneath can do an equivalent of this code. So what do you think this will print out? So will it be like curly braces, value, and within them value colon 4.2? Who thinks it will be kind of expected result? No, they're all tricky questions, right? So the answer is it depends. Because we are using locales. And most of the time, oh, well, as they say, it works on my machine. It works fine. It will print value colon 42, which is a perfect JSON, as far as I understand, until someone sets the global locale to something like Russian UTF-8 or other weird thing. And then you get, instead of your nice decimal point, you get a decimal comma, or, I don't know, decimal ampersand or whatever the locale decides to choose for decimal separator. So you can argue it won't happen to me. I'm a responsible developer. I'm setting my locale to C. But in fact, it can happen to you, especially if you're developing a library and you don't want to mess up with the global state. And it happened to me personally. This is a bug report with a very helpful title, Unaccepted Exception. So this happened because the user had an Italian locale, and I was not careful enough to make sure the output is locale independent, and the format I was writing to didn't really allow decimal commas. I would argue that the only reason for the output to be locale dependent if it's displayed to the actual user. If you're writing to JSON or XML or anything else, there are strict rules that you must adhere, and the output should be locale independent. And maybe this should be the default behavior, or at the very least, you should have control over it. And I should stress that this issue is not specific to iOS in fact, this bug report was open to a project where I didn't use iOS, but it's kind of a common problem. And yet another kind of worms called threads. Let's say you want to print something from multiple threads. In this case, we are printing some simple greeting messages from 2 threads, and then we join them. So again, who thinks that it will print something obvious like hello Joe, hello Jim? Who thinks it's an undefined behavior? Well, I think that's a good answer, reasonable answer by default. If you see a reasonably big chunk of C++ code, the default kind of assumption should be, this is an undefined behavior. So like a rule of thumb. But I don't think there is an undefined behavior unless I made some stupid mistake, which is entirely possible. But the answer, again, it depends. And one of the better outputs that I've chosen by running it multiple times and then selecting the one that I liked was hello, hello, Joe Jim. And the reason why I like this particular output is that when I was a kid, I liked to read Robert Heinlein's Orphans in the Sky, which had a two-headed character called Joe Jim Gregory. So note that in case of cout, there is synchronization there, but not on the level of messages, but rather individual arguments that you output, which is a bit of a regression compared to POSIX printf, where you could have a perfect output. So now a bit of alternative history. What would happen if formatting libraries became mainstream and took over the world? Well, not really. This is just an overview of some of the major formatting libraries and some of the limitations of them, which may explain why they've never taken off. So Boost format is probably the most well-known and widely used formatting library. It supports two syntaxes for its format strings: a printf syntax, which you can see in the example below, and a simplified syntax with positional arguments where you can omit type specifiers. And the syntax is very expressive, but somewhat complicated because you can do everything in multiple different ways. Here you have 4 examples that do the same. And although it supports printf syntax, it's not fully compatible, so it's not a drop-in replacement, which kind of undermines the reason to go this way in the first place. But the main problem with Boost format is illustrated on this slide. The performance, code bloat, and compile times are all very disappointing compared to printf. And not only printf. I'll show later more benchmarks comparing to other formatting libraries. Now this is the actual photo of me in 2012 when I ran the benchmark and realized I can't use this library and I have to come up with something else. Another well-known library is fast format. Unlike Boost format, it is reportedly fast. It even has it in its name, which must be true then. But I've never verified it for the reasons listed here. This is a quote from the author of the library. So the kind of features that cannot be accommodated within the design are leading zeros or other padding, octal hexadecimal encoding, runtime width alignment, which seems very restrictive and makes one scratch one's head. So how is it possible? Fortunately, the author came up with a solution with the same article. So the way you work around this limitation is by wrapping arguments together with kind of format specifiers represented in code, so to speak, and pass this wrapper object instead of the actual argument. But now I fail to see how is it better than IO streams. It's even more verbose now. It has some advantages. For example, it's non-sticky flags, but And also we have atomicity, but otherwise it doesn't look very appealing. So, having looked at all the current solutions and limitations, let's take a look at the proposed future, or the P0645R revision number standards proposal text formatting, which is based on the FMT library I've been working on the last few years. And the motivation for this proposal is to have an alternative to the printf family function, particularly sprintf, which is safe, extensible, and fast. Also, it should be interoperable with IO streams. We don't want to get rid of IO streams at all. We'd like to have small code size and reasonable compile times, have some local control, and have some expressive syntax for our format strings. So, as I said, this is not an IO stream replacement, so if you invested in a tattoo featuring IO streams, you won't need to get rid of it or camouflage it with flowers or butterflies. So, all is good. So, let me show you a few examples that introduce the syntax. So the format string use brace delimited replacement field. Like in this example, I think it's pretty self-describing. Also, you can use positional arguments within the braces. You can refer to arguments with their indices starting from 0. And you can use format specifiers similar to printfs after the colon, like in the example at the bottom. Of course, you can have width either specified in the format string, or dynamically you can refer to an argument that gives the output width. And similarly, you can have precision specified in the format string or dynamically. The way you do it is after the point, you specify the width, either literally or referring to an argument. Also, you can use 3 types of alignments. In fact, there are 4 times alignments, but the 4th numeric alignment is complicated, so I won't talk about it in this talk in the interest of time. So we have left, right, and center alignment, which is an improvement compared to printf, which doesn't have center alignment. I've never used center alignment myself, but I've heard it can be useful sometimes. And you can have fill end alignment, which is even more cool. You can do some kind of ASCII art or whatever. You might find this syntax familiar because it's largely based on Python, particularly Python str format, because they also have % formatting, similar to printf. It is more expressive than printf. In particular, you have fill and center alignment, but format specifiers are similar to printfs, and almost everything that you can write after % in printf, you can write after colon in this format syntax, which simplifies migration and makes it easier to learn. But at the same time, the type is optional because we use variadic templates, we know the types, you don't need to repeat yourself. What do you mean by conflict?
So you have F and a float. What if you said S and a float?
If you say S and a float, it will throw an exception. The syntax is so simple that it fits on a single slide. even part of the slide. So I won't go into too much details. There's fill element. I think you got the idea from the examples. It's very easy to parse. Unlike Boost format, it's very consistent and simple. It also supports named arguments in addition to positional arguments. This is not included in the standards proposal to make it reasonably compact, but it can be added later. So the way you use named arguments is inside the curly braces, you give the name, and then in the arguments, you wrap your arguments together with the name in the arg function. And also, someone implemented user-defined literal version of it, which I won't show. But you can find examples on in the documentation and in the paper, not in the paper. Sorry. So why do we need the new syntax? Why not just use printf? So the reason is that we'd like to avoid all the legacy stuff, all these horrible macros and things like LL and PRIU64, which is not even correct here because this is a signed integer. So instead, we just want to write curly braces and let the compiler figure out. Unless we want to customize our formatting, then we use colon and say how we want our nice arguments to be formatted. So we want the specifiers to be semantical, to convey formatting information, not type information. For example, D means decimal formatting, not decimal int, if you see the subtle difference. And also something that I call bring your own grammar. So you as a user can extend format string grammar for your own types. And I show how to do this in this slide. So the replacements field consists of curly brackets, the argument ID, which can be an index or a name, followed by colon and format spec. And format spec is well defined for standard types, well, built-in types. But for user-defined types, you can interpret it however you like and write your own parser. The way you do it, well, the way you used to do it, because the extension API is changing, was to provide a format value function which took a buffer where you wrote your output, the argument. In this case, I just pass a time TM object, and a context. The context provides access to the portion of the format string being parsed and other arguments. Why you need other arguments? For things like dynamic width or dynamic precision. But if it sounds too complicated, then you don't have to do this. You can just implement overloaded operator less or insertion operator, taking OStream and your object of your type, like standard IOStream way of implementing formatting of your types, and it will fall back to this operator. So why this particular syntax? It has been proven to work. So Python designed this mini language, went to great lengths to implement it and test it in production, and it worked out very well. They wanted to deprecate old %printf-like formatting, but they didn't, but for compatibility reasons. But they are in a more difficult state because % formatting in Python is less broken than printf in C and C++. It's just a little bit broken. So there are fewer reasons to migrate to the new. There were fewer reasons to migrate to this new syntax, and still it was very popular. It was so popular that other languages like Rust adopted it. And there are several popular C++ implementation, the FMT library I'm talking about, and Foley format. And the API is fully type safe, no varargs nonsense, just variadic templates. So we have the format function, which is the main API function, which takes a format string and arbitrary arguments and returns an std string. If you want to be efficient, you don't want to allocate std string, maybe you want to write to a buffer allocated on stack or something, then you can use the format2 function, which takes a buffer and again a format string and arguments. So the memory management is automatic, which prevents the whole range of errors. So the buffer concept represents a contiguous memory buffer memory range with efficient access with only one call, a virtual function call if you need to grow. It can have limited capacity and report an error on growth, or it can grow dynamically. And it has also an associated locale. So here is a simplified version of the buffer class. So we have size, capacity, resize, access to data. This is very simplified, just to give an idea. And the only two virtual functions, one when you hit the capacity, you call grow, and either reallocate or report an error, and also a virtual function to get the locale. So now let's go a little bit deeper and take a look at the format function, how it is implemented. And if you look at it, it just forwards to vformat, which is very similar to printf, vprintf in some sense. So, so format calls vformat with the same format string, and it wraps arguments in an object called argstore, which represents an array of references or copies, if the argument is simple, of reference to arguments. And to build this argstore, we call makeArgs function. And the vformat function takes not argstore, but the kind of view of this object, which is similar to, let's say, array view. And notice that vformat is not parameterized on the types, which might be surprising. And why is it so? So this slide shows the kind of implementation details, but I think it's still interesting. So if we have small number of arguments, we can take all the types together and pack them in a single integer, and store a pointer, and have a pointer to an array of pointers or copies of arguments. So argument store can be thought of as an array of variants. And on the left is kind of compact representation of it, and on the right is expanded representation if the number of arguments is big and they don't fit, all the types don't fit in one integer. So why do this? It helps greatly with compile times and code bloat. It makes the per function binary code very small, comparable to printf. So when you call printf, you often have an integer passed representing the number of arguments passed anyway. So here we have the integer representing all your argument types. So you have similar binary code. Printf is a little bit better because varargs pass more stuff in registers. Another thing is that this kind of type erasure method prevents code bloat. So instead of instantiating all your formatting code on all combinations of arguments, you have just one instantiation. So why do you need all this stuff? Let's benchmark and see whether it really helps or it's just hand-waving. So I wrote this little benchmark, which might be a little bit cryptic, but let me guide you through it. So what it does, it calls the format function for 125 combinations, different combinations of argument types. So this gen args function at the top just calls f with 5 arbitrary objects. The only thing, they just need to be of different types, and then we combine them. We're doing all possible combinations. So 5 to the power of 3, we have 125 combinations. And now what do we compare it against? We can measure our implementation, the FMT library, but I don't want to go and re-implement everything, passing the parameterizing everything on templates. Moreover, I can do it inefficiently, intentionally, to show how good my method is. Fortunately, Foley format comes to the rescue. They did exactly that. They passed all the arguments throughout the formatting code, and that's what we're going to compare against. So this is optimized Clang build with ndebug. Everything is linked dynamically. And as you can see, there is a tremendous improvement both in compile time and binary size. So the compile time is roughly 6 or something times better compared to Foley. When we apply this type erasure technique. And the binary code size is by the order of magnitude better. And this is just formatting code. So I don't know about you, but I don't want 100 calls to formatting function to take 1 megabyte of space. So what we can learn about it, I think the lesson is use variadic templates judiciously. Don't pass them unnecessarily throughout all of your code. So a few more benchmarks. So this one is interesting. This tries to be realistic, unlike the previous one, which tried to fit on the slide. So there are 100 translation units with 5 calls to formatting functions per translation unit and no other code. This is optimized build. And as you can see, boost format goes through the roof. The FMT library, which is the basis of the standards proposal, is a little bit worse than printf. It used to be better before I switched to string view, because now we have to pass an extra size argument compared to previous when we just passed an null-terminated string. There is a trade-off. Now the API is more convenient because you don't have to pass a null-terminated string, but you pay a little bit for it. But I think the price to pay is very little, and if it only matters if you operate in a very resource-constrained environment. In this case, you can obviously provide overloads, taking null-terminated strings. So, one thing to mention is Foley format doesn't perform that bad here, because there are fewer combinations of types. So there are only 5 different combinations of types in this benchmark, unlike 125. But it's still quite big difference. Here's a benchmark showing compile time performance. Unfortunately, with compile time, there's that much we can do. So printf beats everyone, obviously. I think we can get to the level of IO streams. In fact, it used to be on the level of IO streams until some recent regression, and I think we can bring it back down. But it still performs significantly better than other formatting libraries. And a lot of efforts have been put into optimizing compile times, particularly by Dean Moldovan, who has done great research and investigated different ways of optimizing compile times, and even put together these graphs of compile times over the number of arguments. This is on Clang. And the way it was optimized is by replacing template recursion with the variadic array initialization. Interestingly, it didn't give such a big improvement on GCC, only on Clang. Also, it's more noticeable if you use very large number of arguments, like 10 or 12. Now, more kind of traditional benchmark runtime performance. As you can see, FMT performs maybe within 10% compared to printf, and better than IOStreams and other formatting libraries. IOStreams perform, for some reason, particularly bad on this platform, which is Mac OS with Clang. On Linux with GCC, the difference was not that profound. And one thing to mention is that there is nothing in the design of the library that makes it impossible to beat printf. In fact, this particular benchmark is largely dominated by formatting of floating point numbers. And for floating point, FMT currently falls back to sprintf. So it cannot be better than printf. But for integer formatting, I showed in some other benchmarks that it was possible to beat printf, even with allocation of string. So, and you can, of course, write your own formatting functions similar to format. Let's say you want to write a function that takes an error code and a format string and some arguments and writes these to a log. So you can either make it variadic if you don't care about compile times or anything, or you can apply the same technique to your own code and get the same benefits. So work in progress is separation of parsing and formatting in the extension API. So instead of format value function that I showed before that does everything, parsing and formatting, we want to be able to specialize this formatter object, have a separate function that does parsing, separate function that does formatting, and between these two, you can store the state in the object itself. And you can reuse standard formatters. You can, for example, inherit your formatter from formatter int and use get the same parse method and only, let's say, provide the format method. For example, if your object is just some kind of wrapper around int. Other things I'm looking into is compile time format string checks and range-based interface. So let's take a look at the new extension API. Here's a little example. Let's say you want to format a vector of some objects of arbitrary type. So you So you specialize the formatter struct and inherit it from the formatter T. And you don't need to provide the parse method. Let's say you just want to reuse the parsing for the of the format string for the vector from the formatter of T. So you only provide the format method. And the way you implement it, you just write to a buffer a brace, delimited, comma-separated list of values. And you just delegate all the work to the formatter of T. And it's very simple. It fits on the slide, and it can be used as shown below. Of course, if you want more advanced features, you can have a different syntax. You can implement your parse method and, I don't know, customize separator instead of hard coding comma here, but that's all up to you. So, the migration. Will we ever be able to migrate from printf? I think that it might be possible here, some of the ideas. So there is an easy mapping between the printf and this mini language. And we can come up with a compatibility library which with printf-like semantics, particularly that returns error codes, and in other ways it's similar to printf and maybe even well, we won't make a drop-in replacement probably, but we can have a tool like clang tidy, which goes over your code base and transform literal strings into this new format. So with this proposal, I went to the Toronto Standards Committee meeting and presented, and my main goal was to get an kind of initial feedback and understand whether people want this in this standard. Should I work on this or go on with my life? But unfortunately for my life, it was fairly well received, and I've been encouraged to continue, and I'm working on a revision of the proposal. So a little bit about the library itself. So you can find it on GitHub. fmtlib/fmt. There is also a website, fmt.net, with the documentation. There have been many contributors, which I'm very grateful to. And some people took time and packaged the library for all major Linux distributions for Homebrew and NuGet. And you can find the implementation of the standards proposal in a separate branch called std. A bit of history, more history. So it started in 2012, and originally the library was called CPP format. It was inspired by formatting facilities in Clang. That's kind of surprising. I don't even remember what the facilities were. I just remember this fact. And back then, the library looked completely different. It didn't use variadic templates. It used a weird operator overloading API until I figured out how to emulate variadic templates with variadic macros for compatibility with C++ 98. Since around mid-2016, main focus was on the standards proposal. And that's why you don't see very many commits or activity in the timeline, because this shows the master branch and all the work is done in the std branch. And there's been a lot of projects using FMT. Here's a small selection. One in particular that I want to draw your attention at is spdlog, which is a great logging library. So many people don't even realize that they use FMT. They get it through SPD log, which is fine by me because I get fewer bug reports. No, all the bug reports end up in FMT. The author of SPD log is very thorough. So thank you for the attention, and if you have any questions, feel free to ask.
Yeah, I have a question.
Yes.
About formatting the floating point numbers. Isn't there like another way to do that without going to sprintf, like a standalone library? I'm not an expert. I think I saw something that's not going through CLib.
Yes. So the question is whether there is another way to do formatting of floating point numbers without going through sprintf. So yes, for example, we can implement Grisou algorithm or use a double conversion library, which does this and not rely on sprintf. That's actually one of the items on my to-do list. Maybe I'll do it sometime.
Another question, I was just looking through the GitHub implementation for common compile time bottlenecks, and you're not doing a lot of template metaprogramming. Do you know what's taking a long time in compile time?
So the question is, do I know what's taking a long time in a long compile time? I haven't looked at it recently. Last time we looked at it, there was a problem when we used the recursive kind of template stuff. Right now, I'm not sure what exactly contributing to compile times. I would appreciate if anyone knows a good way to debug kind of perf compile times.
I think there is a Clang extension, but
yeah, it would be interesting.
There exists some Clang extensions to help to allow you to do static checking of things, so you can flag incorrect format strings at compile time. Have you explored any of those?
If I understood your question correctly, there is a Clang extension to check format strings at compile time.
It allows you to write a function that would check them.
So unfortunately, as far as I know, it only works for printf syntax.
There's a Clang extension to let you specify your own custom function.
There's a Clang extension that specifies using your own function. No, I didn't know about that. It would be interesting to look into it. Yeah, thanks for letting me know.
I was wondering, can you hear me?
Yes.
I was wondering if there's any kind of improvement that you could make when the format string is a const expression, so that more of the kind of parsing of the format string happens at compile time as opposed to runtime. And taken to its logical conclusion, if you say hello string and the string is world, that could just compile down to hello world and do nothing at runtime.
Yes, in theory. So the question is, are there any optimization we can do for compile const expr strings and arguments? For example, if we have both the format string, if we have everything const expr to do formatting at compile time, basically. Right now, I'm only looking at compile time checking of format strings, but in theory, I think it should be possible to do parsing and at least construction of the format object at compile time, and maybe even formatting itself, but there's still a lot of work to do.
Thanks.
Yeah, I guess the problem just sort of seems interesting. I guess a few of the questions have been related to it. Do you kind of have a plan of attack for the situation where string literals pass, because it's pretty tricky, because once you pass something by value into a function, like in the body of the function, you can't really assume that it's a const expert. You're not going to be able to like static assert with it. So I don't know, like is the plan to like have some string literal type that you pass in as a non-type template parameter or something like that? I mean, do you have a plan of attack yet, or not really sure?
If I understood correctly, the question is how do I plan to handle the const expr format string, right?
Like checking it at compile time.
Yeah, checking it at compile time. That's actually a big problem, and I'm not sure yet how to do it. I would appreciate someone who has experience with const expr and compilers. If they have any ideas how to do it, let me know. Unfortunately, we've run out of time. So if you have any questions, feel free to find me and ask everything. Thanks.